Hey guys, thanks for bearing with me during this coronavirus edition of Gears and Gadgets, being brought to you from my studio personally. Um, I hope this is an adequate substitute for what I'd like to teach you guys in person. At least if anything, you get a little behind the scenes peek as to what I do in here a little bit, maybe. See some of my crap. Keep all my crap well organized and all over the place. So, I guess we should get on with it. Light emitting diodes, LEDs, we see them everywhere and they come in all sorts of shapes and sizes. Um, some of them are ultraviolet, some of them are infrared. They all come in a variety of colors, some are multicolored. They can produce a variety, a whole spectrum of colors. The important thing to remember is that they're polarized. If you want them to light, you have to have them pointed in a specific direction in reference to your positive and negative points. At the bottom you see the schematic. That's the orientation in which you'll see it drawn out. And we'll talk about how to identify which is the positive and which is the negative side of the LED in just a minute. When you buy them, they are always marked with their forward voltage and their forward current. Those are the maximum ratings you'd really want to run them at. Anything more damages the LED. And if you need to supply more voltage in your circuit, you can use a resistor to limit the voltage and the current to the proper amount to provide to the LED. If you put them in backwards, they won't light up. It won't necessarily damage them. You can use them in that way on purpose to rectify an AC current into a DC current, which we'll talk about at a later time. But it's best to protect them with a resistor, even if it's a small one, in case of an overvolting or an overcurrent situation. So earlier I mentioned that LEDs are polarized, meaning there's a positive side and a negative side, meaning one side should be towards the positive side of the battery and the other side towards the negative end of the battery. In your classic LED that you would buy out of the store, it sort of has a bulbous type shape, a nice round top, and it'll have two legs. A short leg that's negative and a long leg that's positive. If these legs are cut, let's say you scrapped it out of a different object, you can look at it from the top. If you see this rim around the LED, at the leg that is the negative leg, there will be a flat sort of ground into that side of the LED, and that leg that's towards the flat side will be the negative leg. If you have an LED that's not round and has its legs cut off, all you can do is experiment and pray. But those are the general guidelines for figuring out which polarity works. So resistors literally resist. They impede the flow of electrical current. It's measured in a rating called ohms, which is the omega sign. And the more resistance you add to a circuit, the lower the amperage flowing through that circuit. The reason these are going to be important for us right now is that resistors we use to protect our LEDs from too much current. More resistance, less current. We need low current for our LEDs, so we'll be using resistors to restrict the current and the flow of power to the LED. They come in all sorts of different sizes. The size means almost nothing to the amount of ohms. Mostly it has to do with the watts that it can take, the amount of power it can take before overheating. Starting from the top to bottom, the 33,000 ohm resistor looks a lot like the 3,300 ohm, and a lot smaller than the one that is actually higher than both of them, the 47,000 ohm. So learning to read their colors is important with this normal type of ceramic resistor. These larger types of resistors are usually printed onto them, 1 ohm, 0.1 ohm, and then these fancy ones, which I'll talk about in a simple circuit later, these are resistors that vary with the amount of light that makes contact with them. So this one can be as low as 5,000 ohms and as high as 250,000 ohms. When you read a resistor, you want to hold it where the gold or silver line is on the right. That's your tolerance stripe. It tells you the tolerance of the resistor, meaning plus or minus 5% if it's gold, 10% if it's silver. Not usually a huge factor for you, especially right now. There's always 4 stripes. The first 3 indicate numbers. They're using colors as numbers, and each color, dependent upon where they are, means a different type of number. The same number, but it uses it in different ways. So the first one here is a number 4, yellow, followed by an orange, which stands in for 3. Red in the third line, usually in any other line, means 2, but because it's in the third line, it's asking us to essentially add 2 zeros to that number. So reading this across is a 4300 resistor, which is a 4,300 ohm resistor. So that's how you would read a resistor like that. We'll talk about the colors in just a second. So, reading resistors. Resistors are color-coded. Every color literally stands in for a specific number. Those numbers change their meaning based on where they are on the resistor. So if in the first 2 stripes you have a brown, red, something resistor, that is a 1, 2, something. The third stripe is that something. If it's a brown, red, orange, let's say, that's a 1, 2, and then the third stripe's your multiplier, so that orange doesn't stand in for 3, it stands in for 3 zeros that you'd add on to those first 2 numbers. So a brown, red, orange is 1, 2, 1,000. So that's a 12,000 ohm resistor, or 12K, like money. 12,000, 12K ohm resistor. It goes that way through the entire spectrum, from brown to white, or black to white. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. The third stripe stops at violet, because after that, that's a million. So that's a 1 mega ohm resistor. After that, you don't really need to worry about it. There are no corresponding third stripes for violet, gray, and white. So at that point, it's just the weirdness in black. Black, instead of adding a 0, you move the decimal place over. So if it was a red, orange, black resistor, that would be a 2.3 ohm resistor. So those are for much smaller ohm ratings. We're also going to be dealing with one other type of resistor, and those are potentiometers. They're variable resistors. They're resistors that can change how much resistance they give you depending on how you hook up to them. They have 3 pins coming out of them, unlike the other resistors, which you noticed only had 2. And they come in, again, a variety of sizes and shapes that mean almost nothing when you actually look at their total resistances. The biggest one here is actually not the largest one of maximum resistance. That's this guy down here, which is actually fairly small. So always check to see how much the variable resistance is. It's always labeled with the maximum amount of ohms. So it can go from that number, 1 million ohms, which is 1 mega ohm, to 0. So that's the range. Labeled with its maximum, but it can also go all the way down to 0. The same thing with any of these other types. I'm also labeling them longhand and shorthand. So this is 1 million, but if you see it written out, you'll most likely see 1 M and then the ohm sign. Just as you would see 50K, the ohm sign. It works a lot like money in that way. All of these types of things, if we take a look at them, they all have knobs that rotate, little knobs. This one's pretty easy to grab, something like this you'd find in a stereo. Other ones like these types you might find in smaller electrical devices, the volume knob on old style CD players, Walkmen, all different sizes, all different types of resistances, but on the inside they all look the same. There's a ring essentially of resistive material going from one lead to the other. All resistance. Essentially it's the same material that's inside the other resistors. The third pin to the potentiometer is where you hook up your voltage to vary it with this wiper that lives on top of this rail. So as you travel from one side to the other, you're literally putting less resistive material or more resistive material between your contact point and the other contact point. So what this means is that if I hook them up to these two, I can vary my resistance, no problem. If I hook them up to these two, I can vary my resistance. It'll work in the opposite direction. But if I hook my leads up to these two, I will be getting the full resistance of this particular potentiometer because I'm not hooking up to the varying part of the variable resistor. So here's the simplest series circuit you can pretty much construct. Any circuit is a way for the electrons to travel from positive to negative. Conventionally, particle physics says they travel the other direction. Don't worry about it right now. In this configuration, in both schematic and in a real-life practical version, I have an LED and a 330 ohm resistor in series with the battery. These two AA batteries are providing me 3 volts. They're in series as well, so they combine their voltage to provide 3 volts to my LED. It needs about 3 volts. I don't technically need the resistor because it requires 3 volts. It's just for protective measures, for good measure. It just makes it slightly dimmer, and by touching them together I can complete the circuit. And inadvertently we've made ourselves a little touch switch here. You can make lots of versatile means of interacting with your electronics, and this is all just taped down on a piece of paper together. This 330 ohm resistor, this is the schematic for a resistor, just a little zigzag, and then usually denoted by its ohm rating of resistance. Your LED points negative, and that's the schematic symbol for that. So we're looking at essentially mirror images of the same thing. A series circuit is always just a straight line between positive and negative with everything existing on that single path. You can think of it sort of like this underline here. Everything just lives on that line. And here's a simple parallel circuit. Parallel circuits differ from series circuits in that the loads applied to the circuit exist between the positive and the negative simultaneously. They're being delivered their power at the same time, not one before the other. So in this particular schematic we have two LEDs and 2 resistors in parallel together, but each one of these sets is a small series circuit. So this is a series parallel circuit, and over here the same configuration in practical terms, and I'm using the connecting of the negative pole to everything to make the circuit complete. Another fun touch switch. So you can think of it as though the positive and the negative ends are being connected to each one simultaneously, delivering the power at the same time, sort of like up here, this parallel circuit. You have these LEDs and resistors getting parallel power from the hot or positive and the ground or negative at the same time, every one of them. Neither one is dependent upon going through the previous load to get to the next one. They're all getting power at the same time. Just like this schematic, both of these sets of series circuits are getting their power at the same time. So now we're going to work with these components in a practical application in a way that you'll be able to do when you get your kits in the mail. Right now I've got two AA batteries, again in series, making a 3-volt circuit. I have that hooked into my breadboard. This breadboard, this is a means by which we're going to be able to prototype and figure out circuits without actually having to do any soldering whatsoever. The components of the breadboard operate like this. We have these long columns on either side of the breadboard, and each one of these dots is connected to each other one of these dots. This outside lane is separate from the inside lane, but every connection in that lane is connected to each other on both sides of the board. What I've done here with these two wires is connect the outside to the outside and the inside to the inside, so that when I provide power to either one of them, I'm getting power everywhere. So as I construct my circuit, I don't have to choose which side to go to retrieve my power. I have options on both sides. Now that I have my batteries plugged in to my long rows, I can start to work with these smaller sections. They all have numbers so I can keep track. All of these are only connected top to bottom in this orientation. So let's say row 8 is connected to every other dot in row 8 and only that row. They also do not jump this center gap and continue on. So number 8 here is separate from number 8 here. And knowing this, we can start to manipulate where our power is going and to which appliances they're going to. I'm going to use a handy dandy LED. Looking at its legs, I'm going to know that this one is the short one and that's the negative side. I could also look for the flat that's on the LED, and it is on that side. So I'm going to make sure that my flat, my negative leg, is plugged into the negative side of one of these rails. Doesn't matter which one. And then I'm going to bring it out into the smaller columns here. I'm going to take this opportunity to play with a light-dependent resistor. Connect that from the same row as the other leg of the LED to the positive side of the battery on the other side. And there we go, it lights right up. The beauty of this particular type of resistor is that by varying the light, I can vary the amount of power going to the LED. So it can almost act as a small switch. It'll act as a sensor with a microcontroller like an Arduino. But it's a way that we can start to get slightly more fancy with how we're using our light. I wonder if you guys can even see that. I guess you can kind of see that getting dimmer and brighter. I'm going to shut the lights off in the studio so that you can get a slightly better look. You can see it's very dim right now, but with this flashlight, I can start to increase the amount of power flowing through it to a pretty large extent. So that's the interesting power of light-dependent resistors. They can make interestingly interactive circuits. So that covers the basics of DC circuit making and most of the appliances and equipment we'll be using from the get-go. If you guys have any problems, don't hesitate to email me and order your Arduino kits so that next week we can get started with those. I'll make another video that should hopefully help you guys through the process. Be safe, stay healthy.